Hi everybody, this is the lecture about gravitation. Let's get into it, starting with Isaac Newton, the guy who found all this stuff. So it's just a reminder of all of his accomplishments. So he refined and expanded Galileo's ideas. He overthrew Aristotelian ideas of motion. He did his first 3 laws of motion. That was inertia, F equals ma, and for every force there's an equal and opposite force. He claimed that knowledge was a result of a long thinking process. He developed laws of optics and many other things. And what we're going to do now is Newton's law of gravity. Okay, so this is a sort of story of how he came up with it. The important thing is that we have the universal law of gravity. And everything pulls on everything else. That's important. So everything that is out there pulls on everything else. And every body attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. So that's force of gravity is proportional to the 2 masses multiplied together divided by the distance between them squared. Okay, so if we have m1 here and m2 here separated by a distance d, then the force between these 2 objects is big letter G, which is a constant, times mass 1 times mass 2, all over the distance between them squared. And this big letter G is just a number with some units attached. It's always a constant. Okay, let's look at this. Which statement is true regarding the universal law of gravity? Force is proportional to both masses and to the square of the distance between them. No, it's inverse square. Force is inversely proportional to both. No, it's proportional to both masses. Force is proportional to the square of the distance between. No, proportional to the inverse square of the distance between them. Force is proportional to both masses and inversely proportional to the square of the distance between them. That sounds right. D. Okay, good. Okay, the next one, the universal gravitation constant G, which links force to mass and distance, is similar to the familiar constant pi g, acceleration due to gravity, speed of uniform motion. Well, speed of uniform motion can be anything, so it's variable depending on the situation. Acceleration due to gravity is variable depending on the situation. G, which is 10 meters per second on Earth, but could be different in different places. Really, it's like pi, the thing that never changes. It's the same for every circle everywhere. The force of gravity between 2 planets depends on their masses and distance apart. That's true. Atmospheres, no. Rotational motions, no. Looks like A. Masses and distance apart. That's based on this. Masses, constant, and distances apart. Okay. If the masses of 2 planets are each somehow doubled, the force of gravity between them, well, if both masses are doubled, then you get two doublings, which gives you 4, which is a quadrupling, so B. Okay. If the mass of one planet is somehow doubled, the force of gravity between it and the neighboring planet, well, if we look at if one of these 2 masses here, one of them is doubled, then its value is doubled here, so the force is doubled. Okay, so it should be doubles. Which of the 2 methods is more correct for calculation of the force of gravity acting on the object at the surface of the Earth? So either of these will work. This is often more convenient, but both of these will work. So I think both are correct. Okay. Which of the 2 methods is more correct for calculation of the force of gravity acting on the object far away from the surface of the Earth? So this one's not going to work because this is only for the surface of the Earth, where this is 10 meters per second squared. This is the universal law, so this has got to work every time. So it's going to be A. Okay. Okay, this is a derivation of G. You don't have to know this. And G being the 10 meters per second squared on Earth. So you take the universal law of gravitation, and you, let's see, we put in the mass of the Earth for 1, the mass of the object for the second mass, and the radius of the Earth, because we're on the surface, for the distance between the objects. So you got this big massive planet, little object on the surface, distance from the center is the radius of the Earth. And then we notice that G better be big G times mass of the Earth divided by r squared of the Earth. Okay, and therefore, so G is this stuff. And if you plug in the numbers, it's indeed 9.8 meters per second squared, or just 10 approximately. You don't have to know this derivation, but this is where G comes from. Okay, the inverse square law, which is the thing that the force of gravity goes as 1 over the distance between the two objects squared, has some geometrical foundations where the radius, if the radius is doubled, the surface area of a sphere is quadrupled. So this is why as you go farther and farther away, as two objects move farther and farther apart, the gravity force goes as 1 over r squared, or 1 over distance squared. Okay, gravity and centripetal acceleration. So we've got the Earth and the Moon. We know that the Earth and the Moon orbit one another. Well, we think of the Moon as orbiting the Earth, but they both orbit one another. So the Moon is going in a circle around the Earth. And the centripetal, we need a centripetal acceleration to do that. The force that provides that is gravity. Okay, so the force centripetal on the Moon is equal to mv squared over r is equal to mac. This force right here is going to be due to gravity of the Earth. Okay, let's talk about weight and weightlessness. So the apparent weight is the force an object exerts against a supporting surface. Okay, so standing on a scale in an elevator accelerating upward, less compression on the scale springs, weight is less. Standing on a scale in an elevator accelerating upward, more compression in the scale springs, weight is greater. At a constant speed in an elevator, no change in weight. So the apparent weight you feel depends on how you're accelerating around. So you can feel this on an elevator. When you start accelerating up, you're heavier, and then you go to constant speed, you're the normal weight, and as you slow down, you feel a woo, and you feel lighter, and that's apparent weight. There's also weightlessness. If you're in free fall, you have no weight. You can just move around, like if you're skydiving or something. You can move around and you're in weightlessness. Not quite with skydiving because there's the force of air friction. But if you could ignore that, like in space, you'd be completely free floating and weightless. Okay, so here's an elevator. If you're sitting in a stationary elevator, you got normal weight. If the elevator starts to go up, you get greater than normal weight. If it starts to go down, you get less than normal weight. If the cable snaps, you're at 0 weight because you're in free fall. Okay, so recall that the scale reads the normal force that it exerts on a person. We call that apparent or effective weight. Assume the mass of the person is 60 kilograms. Okay, so this person is sitting in a stationary elevator. We know that the sum of the forces is 0 because she's in equilibrium. So the normal force, which is up, and the weight of her, which is down, are equal to 0. And the normal force is equal to weight, which is 600 newtons. So that's her apparent weight. If it starts to accelerate up, her normal force or apparent weight is going to go up as well. Because if she's accelerating upward, then the sum of the forces is now ma, not just 0, because it's not in equilibrium anymore. So normal force up minus weight down is m times a, which is positive. And we do some rearranging here. If the acceleration is, does it say here? They're just going to plug it in for us, 2 meters per second. So 600 newtons plus 60 times 2 meters per second, that's her new weight, 720 newtons if she's accelerating up at 2 meters per second squared. Okay, and this is the opposite direction. If she's accelerating downward, then same process. The force of the normal force, the apparent weight, will be 480 newtons less than normal. And if it snaps, then the sum of the forces will be equal to ma. Her weight will be equal to mg. The acceleration is minus g, so there's no normal force. So her weight is exactly accelerating her downward. So there's no normal force, and so there's no apparent weight. Okay, when an elevator accelerates upward, your weight reading on the scale is greater. Not less, not 0, not the normal weight. It's going to be greater. When an elevator accelerates downward, your weight reading is less. Okay. When the elevator cable breaks, the elevator falls freely, so your weight reading is 0. That's weightlessness. If you weigh yourself in an elevator, You'll weigh more when the elevator moves upward, moves downward, not sure. Accelerates upward, sounds right. That's what we want. Okay. All right, ocean tides. So ocean tides are caused by the Earth and moon and sun relationship because they all have gravitational attraction to one another. So here's a picture of the Earth, and here's the simple scheme of the oceans here, and here's the moon. And both of these, all the liquids is attracted to the moon just slightly, which causes this bulging effect of the liquids in the ocean, which causes the tides. And when the moon and the Earth are and the sun are all in line, we get strong spring tides. That's what they're called. And when the sun and the Earth and the moon are perpendicularly aligned, then we get weaker neap tides. Okay, gravitational fields. Now, every mass creates a gravitational field. It looks like this, and it's a bunch of arrows pointing in towards the object. Okay, so every object has a gravitational field. The Earth is really strong gravitational field. This bottle of water has a gravitational field, but it's really small. We can think of it as an attractive field pointing inward toward the object from every direction. And in this picture, where the lines are more crowded, it's stronger. And when out here where the lines are weaker, when the lines are more spread out, it's weaker. Okay, so you can read this. The important thing here is this graph right here. Outside the Earth, so this is the Earth, and this is the radius of the Earth. And then this is a graph from the distance from the center of the Earth and the strength of the gravitational field. Starting from the center of the Earth, there's no gravitational field because all of the gravity cancels out at the middle. And gravitational field grows linearly until you hit the surface, and then it decreases as 1 over r squared, according to Newton's law of gravitation. Okay, so this is important. Linearly grow from inside the center of the Earth until you get to the surface, and then decrease 1 over r squared as you go out. That's the gravitational field. Now this is Einstein's field of theory of gravitation, and this is about space and time warping to create gravity. We're obviously not going to get into all of that, but we can use this analogy of like if you have a sheet and you put balls on the sheet of different masses, then each ball will warp the sheet in a different amount. The heavier the ball, the more warping. So this ball, which is 10 kilograms, is going to warp this sheet quite a lot. Heavy gravity, lots of gravity. Whereas this lighter ball will only warp the sheet a little bit. So that's got weak gravity. So we can think of Einstein's theory as this sheet as space-time, and the mass of the objects is determining how much each object warps space-time, which is the gravitational field. And then black holes, which is infinite warping of the sheet. So we get this singularity, which is a point of infinite mass density, which completely warps space-time until it's infinite, and we don't actually know what happens at that point. And we can actually see this in Newton's law. If you were to decrease d to 0, the force would go to infinity. Okay, what would happen to Earth if the sun became a black hole? Well, if the sun became a black hole, we'd start getting light, but it would stay in orbit because the mass of the sun isn't changed. So it would break away from the attraction of the sun. That's not true. Mass of the sun stays the same. It would be pulled into the sun. It's still we're pulled into the sun today. It just wouldn't be any different. It would become a black hole too. That's not true. So none of the above. Okay, nothing would change. Well, I mean, we'd all die, but the Earth would stay in orbit. Okay, wormholes. Wormholes, okay, these really theoretical things about space-time warping so much that we can create bridges between different points in space. If you're interested in this, let me know. Send me an email. Dark matter, dark energy are theorized types of matter that are needed to explain gravitational effects we see in the wider universe. So dark matter is an undetected form of mass that emits little or no light, but whose existence we infer from its gravitational influence. And we see this in galaxies and stuff. And then dark energy is an unknown form of energy that seems to be the source of repulsive force causing the expansion of the universe to accelerate. Okay, so these are two different things we've inferred, but we haven't detected yet. Okay, and then contents of the universe. 4.4% of the universe is ordinary matter, 23% dark matter, 73% dark energy. Okay, so what's the evidence for dark matter? One of the big things is these gravitational rotation curves. So according to theory, the gravitational rotation curve should drop as 1 over r squared, but instead it stays flat. So if we we go back to this. According to, if visible matter was the only thing out there causing gravity, we would expect this shape. Instead, we see something that's flat. So there must be missing mass. Is that what we're saying? So this is we would expect something like this, but instead we get something like this flat. So there must be missing mass. We call that dark matter. And we still haven't detected it yet, but we know it should be there. Okay, so the mass of the Milky Way, it's huge. And according to our understanding, here's the mass. This is Milky Way, this blue thing right here. And the dark matter is this halo around the galaxy. If we look even bigger, we zoom out, we look at galaxy clusters. The amount of mass is 50 times larger than the mass of the stars in the clusters. Okay, how do we know all this? With clusters of galaxies, we look for gravitational lensing, which is gravity warping light around mass clusters. Very much like light bending through water or a liquid. Okay, here's some pictures of gravitational lensing. We can turn this into a measurement of how much dark matter there is in a particular galaxy cluster. And what might dark matter be made of? We don't know. This is some speculation here. It doesn't seem, there's a lot of things that we thought it was in the past, but none of them match what we see, and none of them have been detected. So that's currently an unknown problem in science. All right, let's do some check yourselves. Gravity was first discovered by early humans. These people, everybody knew about it. Everybody knows about it from birth. So early humans. Legend tells us that Newton realized that the idea of an apple in free fall applies to all apples, the moon, all of them. He said both of these. The moon falls towards Earth in the sense that it falls with an acceleration of 10 meters per second squared. No, it's too far away for 10. Beneath the straight line path, it would follow without gravity. That sounds right. So if it's moving this direction, gravity's pulling it down in it's beneath the straight line path. Definitely not both of these. No, maybe not neither of these. Let's go with the second one. Okay. Planet remains in orbit while falling around the sun due to its tangential velocity. That sounds good. Zero tangential velocity. No, it definitely has some acceleration. That's only on the surface of the Earth, so that's not relevant. Centrifugal force, that's not a real force, so it's got to be tangential velocity. The gravitational constant G in Newton's law of gravity produces the correct units of force in Newton's equation. That's true. Indicates the strength of gravity. That's true. Changes the proportion form of the law of gravity to an exact equation. That's also true. So all of these. The force of gravity between two planets depends on their planetary compositions. No, it's going to be their masses, not theirs. Well, the composition, if the composition is different, then the mass might be different. Let's hold off on that. Planetary atmospheres, that's not relevant. The atmosphere doesn't play a big role. It contributes to the mass, but it's negligible. The rotational motions, that doesn't play any role. So I'm not sure. It's either none of these or planetary compositions. And if the answer is none of these, I suspect the composition won't play a part because they'll just say it's just mass. Okay, none of these. And letting the equation for gravitational force guide our thinking, we can see none of the choice valid. Okay, so the reason why planetary compositions isn't because we should be talking about mass only. We don't care about the composition. I was thinking that the composition could potentially change the mass, which is true, but not the direct answer. If the sun were half as massive, its pull on Mars would be half as much, because it's proportional to its mass. Okay. An apple halfway up a tree falls due to gravity. An apple at the top of the tree is pulled by a gravitational force that is twice as much, no, half as much, no, 1/4 as much. It's about the same, right? Because the distance from the center of the Earth hardly changes when you go from the bottom of a tree to the top of a tree. Oh, where am I? Yeah. So it's about the same. It's such a small difference that it's the same for all intents and purposes. Our sensation of weight is due to our sense of mass. We don't have a sensation of mass. Well, sort of. Maybe we do. A sense of inertia, we do. Is due to the force of gravity in a direct way. In an indirect way, it causes the normal force to be there. May or may not be due to the force of gravity. That's true. Sometimes the normal force can be due to gravity, or it can be due to some other thing. Like we're in one of those going in a circle. Remains constant as long as mass is constant. That's not true. So it's like this one. May or may not be due to the force of gravity. Okay. When an astronaut is in orbit, when an astronaut in orbit is weightless, he or she is beyond the pull of Earth's gravity? No. Still in the grips of Earth's gravity? Yeah. In the grips of interstellar gravity? I don't think so. Not sure what that means. And none of these, so I think it's B. Okay. Inhabitants of the International Space Station do not have a force of gravity on their bodies. That's false. They do have a force of gravity. Sufficient mass? I'm not sure what that means. Support force? That's true. They have no support force. They're in condition of free fall. Do not have a condition. They are in free fall. So it's got to be, they have no support force. Okay. The body most responsible for ocean tides on Earth is the moon. We know that. Sun plays a role, but the moon is the primary reason. Okay. Most educated people know what body produces ocean tides, but which pulls more strongly on Earth and its oceans? I did not know this. I just thought the moon pulled more heavily on Earth than the moon does, but than the sun does, but apparently the sun pulls more. Never calculated these numbers. So moon is responsible for ocean tides, but the sun has more. The sun has a stronger force of gravity. Okay. The highest ocean tides occur when Earth and the moon are lined up. That's that one slide where the Earth and the moon and the sun are all lined up. Those are spring tides. When they're perpendicular to each other, those are neap tides. Those are weaker. So lined up. Okay. Tides in Earth's atmosphere are non-existent. I don't think that's true. Exist only during the time of a new or full moon. Not sure about that. That doesn't sound right. Result from the same fit. It doesn't sound right because gravity is always in force. Result from the same physics responsible for ocean tides. That sounds right. Have no effect on Earth's creatures. They may or may not. I'd say number 3. Okay. Compared to the gravitational field of Earth at its surface, Earth's gravitational field at a distance 3 times as far from the Earth's center is about, well, we know it's 1 over r squared, 1 over distance squared. So if it's 3 times, then it's going to be 9 times. So 1/9 as much. Okay. Compared to the gravitational field of Earth at its surface, the Earth's gravitational field at its center is, well, we know that Earth's gravitational field at the center is 0 because all the gravity cancels out there. Okay. Imagine you're standing on the surface of a shrinking planet. If it shrinks to 1/10 its original diameter with no change in mass, on the shrunken surface you'd weigh, remember it's 1 over distance squared, so we're going from 10 to 1. That's a 10 drop to 10%. So it's going to be 10 squared, which is 100, so it's going to be 100 times as much because it's 1 over 10 squared, which is 1 over 100 squared, but it's all on the bottom, and you flip it, and you get 100 times as much. A black hole is a collapsed star. That sounds right. A 2-dimensional surface in space. That doesn't sound right. It's 3-dimensional. Barely visible with high-powered telescopes. I think it's not visible with high-powered telescopes. but I'm not sure about that one. A new form of gravity. No, it's gravity, normal gravity, so it's a collapsed star. Okay. A spacecraft on its way from Earth to the moon is pulled equally by Earth and the moon when it's closer to the Earth. No, Earth is more massive, so it's going to not, that's not true. Closer to the moon's surface, that sounds right. In order to compensate for the Earth's larger mass, we have to be closer to the moon to have equal forces. Halfway? No, since this would only be true if Earth and moon had the same mass. At no point, since Earth always pulls more strongly. That's not true. We can find somewhere closer to the moon's surface where the forces are equal. Okay, and that's it. If you guys have any questions, let me know, and I'll see you for the next lecture.